Hello everybody. Till the last session, we have been focusing on modeling of electric circuits. We went through the process of obtaining the model in the form of state equation, and then we obtained the sinusoidal steady state equation, and then we looked at the model in the form of transfer function, which gives you a much better picture of the pole zero domain. And we saw how it is applied to the RC, RL, RLC circuits. We will be using the sinusoidal voltage source quite frequently in the electrical systems, because sinusoidal voltage source is what is also obtainable from the wall socket. It is also the fundamental source in terms of the motors like the induction motor, the generators, the alternators, all those give the sinusoidal waveforms. So also when we are talking of the transformers and the coils, we talk in terms of fundamentals in terms of the sinusoidal waveforms. So sinusoidal is a pretty important wave shape. So this session will focus on trying to understand this sinusoidal wave shape and the various nomenclatures which are associated with this sine wave. So today we start with a discussion on the sinusoids. So that we try to gain a much better understanding of this type of waveform, which will help us in further analysis and analyzing the future components that we will be discussing later on, which is the transformers in the magnetic domain, the induction motors, the DC motors, and their controls. So sine waves are something that you should become familiar with and very adept at. So if you take a typical sinusoidal waveform, let me draw the x and y axis. So this is the y axis, and then we have the x axis. The x axis is of course with respect to time. Let us draw the picture of the sine wave. So you should also try to practice drawing the sine wave as good as possible, because this is something that you will be using more and more frequently in your future analysis, applications and design with respect to the electrical engineering field. So if we take this sine wave, here it is with respect to the amplitude. Okay. It could be a voltage waveform or a current waveform, and based on that, okay, this can be confused, A can be confused with amps, so I will just write it as a voltage or a current waveform. So let us say we have this sinusoidal picture here. One critical point of the sine wave is the peak value. So this is the peak value, and normally if it is a voltage waveform, we are denoting it by Vm, Vmax or Vp, V peak, depending upon different literatures. They follow different conventions, but we will follow Vm to represent the maximum value or the peak value of the sine wave, and that is exactly this point. And then when you say peak to peak value, peak to peak amplitude, it is sometimes denoted by Vp hyphen P, V peak to peak, and that is from the positive top to the negative bottom the amplitude as shown here. So, this is V peak to peak. Now, this sine wave also has some definitions on the x axis. One of the most important definition is the time that it takes for completing one period, meaning from this, that is, it starts from 0, it reaches a peak, goes back to 0, goes in the negative direction, and then comes up and goes to 0. Then from there on, the same wave shape is repeated on and on, so on indefinitely. So, which means this is one segment which is repeated in a time period t, and in the next time period t, the same wave shape gets repeated, and it keeps on happening after every time period t. So, this is a repetitive waveform, repeats every period. So, this time period t is called the period of the waveforms, is just called the period of the sine wave. This is called the period of the sine wave. Now, let us say the frequency. The frequency at which this sine wave repeats is nothing but 1 by t, and this is in hertz, Hz, after the famous scientist Hertz. Time is in seconds, frequency is in so many cycles per second, which is hertz. Okay. So, we have these definitions of the sine wave as you are seeing it on the paper or on the picture. Now, let us try to get some information which is not directly seen from the picture. One is, now this we stated was the peak, which is Vm. Let us say this is the voltage waveform with respect to time. This is the 0 point, and this is the t by 2 point, and this is the t point. Okay. And the frequency f equals 1 by t hertz. Now, this we would like to draw some conclusions about this waveform in terms of its average value and few other characteristic values of this particular waveform. Now, let us say what is the average value of this waveform. What is the average or the mean, average or mean of this waveform? What do you understand by the average or the mean? It means the area under this curve divided by a base. So, the area under this curve is nothing but this, what is being hashed. This is the area under the sine curve, the portion that is hashed, divided by the base, and the base in terms of the x-axis is t. So, the average value, and let us say V average, is, we have the area under the curve by time base, which is in this case t. Now, if you see the area under the curve, of course, it is evident just by looking at it, as the top half of the sine wave is having a similar curvature and like the bottom half of the sine wave. The top area, because this is on the plus side, this is on the minus side. Okay. So, which means this is an area which is on the plus side, this is an area which is on the minus side, and they both cancel, and ultimately you are going to get 0 at the end of 0 by t, which is equal to 0. So, the mean value or the average value of the sine wave is 0 because there is no DC offset. The top area and the bottom area exactly cancel, and this is a pure AC signal. Okay. However, there are a few modifications of the sine wave that you would see depending upon different circuits. For example, if you pass it through a rectifier, it could be a half wave rectifier or a full wave rectifier, where you will see portions of the sine wave which is coming out. Let me indicate to you, let us say this is T. Let us say the original sine wave was something like that. Okay. For a period, always I am going to draw for a period starting from 0. So, voltage waveform. I could have, let us say, this waveform passed through a full wave rectifier, which means you get an output V out, which is equal to V absolute value, or it is nothing but a full wave rectifier is nothing but having a characteristic something like that. You feed in V, you get V naught, which is equal to absolute value of V, which means, look at this particular effect. What it basically does, this is 0, this is the positive axis, this is the positive x axis, that is in terms of time. Sorry, this is in terms of the input, this is V and this is V naught. So, whatever be V naught is positive, which means if you have V positive, V naught is positive. If V is negative, V naught is still positive. So, that is what this graph represents. This is an absolute value circuit. A full wave rectifier is a absolute value circuit. This is nothing but a full wave rectifier. In terms of wave shape, how does it look like? So, V is like this. What does V naught look like? So, V naught will follow the positive of as is. Once it becomes negative of, negative also is made positive, and this starts coming equivalently positive and then comes like that. So, if this is V, the blue one, the red one is V naught, which is the full wave rectified waveform. Okay. This is the full wave rectified waveform, rectified sine waveform, because we are talking of the sine. Now, what is the average value of this? So, let me make some space here. So, what is the average value of this full wave rectified waveform? So, quite evidently we see that as the waveform is always positive, there is no negative portion, there is no area that can try to cancel out the positive area. There is no negative area which will try to cancel out the positive portion, and therefore, you will have a non-zero average value. So, all are positive. So, therefore, this has an average. So, we average, this case will be the area under the red curve divided by the time base, which is t, and that is what it is here. Or we could also say area under 1/2 of this red curve up to here divided by the time base, which is t by 2, because that is repeating every t by 2 times. So, you could now say the new period is just t by 2. So, area under 1/2 of the red curve divided by t by 2. Now, what is the waveform for the sine wave? So, if you take the blue, that can be represented as V m sine omega t. V m sine omega t is the mathematical representation of the sine wave here. This we saw earlier when we were discussing the subject of sources. Omega is the frequency, the radiance frequency, which is 2 pi into f, or which is equal to 2 pi by t. F is 1 by t into t. So, this would be the equation of the sine wave. Now, let us try to find out the area under the red portion of the curve for 1/2 the cycle using this equation. So, how do you find area? Area under the curve is found by integrating the curve, which will give you the area under the curve. So, let us go to a fresh page. Let me write only the half portion. This is the time axis. Now, we have the full wave rectified waveform, and let us take up to this point, that is t by 2, 0 t by 2 t, and this is V m. So, what is the area under this curve? It is the integral of this curve which will give you the area of the curve. So, the integral of the curve divided by the base, which is t by 2, will give you the average value. So, V average will be equal to integral 0 to t by 2. So, we want to perform the integral from 0 to t by 2, and we integrating the voltage waveform divided by the base, which is t by 2. This is going to give you the average value. So, we know what V is, therefore, V average, which is equal to 2 by t integral 0 to t by 2 V m sine omega t dt, which is equal to V m 2 V m by t. Integral of sine omega t is minus cos omega t by omega and that has to be evaluated at t by 2 and 0. So, which will give you 2 Vm by omega t and minus, now this will be minus cos 2 pi by t into t by 2 minus of minus plus cos 2 pi by t into 0 So, this is going to be 2 Vm by omega t into cos of. So, if you see here, the T2 goes off, this will be equal to minus 1 minus here. So, we have a plus and a plus 1. So, this is equal to 4. So, I am writing it here Vm by 2 pi by t, that is omega into t. So, we have a cancellation of t, this becomes 2 and therefore, this becomes 2 Vm by pi. So, that gives you an average value for a full wave rectified waveform, which is equal to 2 Vm by pi. This is the average of a full wave rectified waveform with Vm as the parameter. So, this is something that you may have to remember. Now, a slight modification to the circuit is a clamper, that is from the absolute value circuit you could use a clamper where the voltage of the sine wave is not passed through an absolute value circuit, but it goes through a clamping circuit such that as long as it is positive you get the waveform, the input and the output follow. As long as the waveform goes negative, the output is clamped to 0 and so on. So, this is a clamper circuit, it gets clamped to 0 and this results in a half wave rectification. So, as the name indicates, it is a only half the wave gets rectified every cycle in a period. Now, what is the average of this waveform? If we are having the peak value which is Vm, we have to find the average from 0 to t. You should see that it is not repeating every half cycle like it was in the case of the full wave rectified waveform, and therefore, we have to consider the whole period. So, in the whole period it is 0 for half the time and it is having an area only from 0 to t by 2. Of course, one could find V average which is equal to 1 by t, which is the base, into the area which is 0 to t by 2 Vm sin omega t dt. This is the average value that you would get for this one. This is, as we see here, that this is not 2 by t, this is just 1 by t, this is for the whole period, but you are integrating from 0 to 2 by t by 2, because from t by 2 to t it is 0 and there is no output which comes into the picture. So, this would give you 1 by T into Vm into minus cos omega t by omega, that is evaluated 0 to T by 2, and this will result in Vm by pi. There is a factor 2 missing with respect to the full wave, which is evident because it is half that area. So, you will get a value which is Vm by pi. So, for half wave rectified waveform, sinusoidal waveforms, the average is Vm by pi. So, this is how you obtain the average. There is one more important feature which is commonly used everywhere, that is the root mean square or the RMS value. RMS value of the sinusoid. What does RMS value mean? Okay, this has a relation to the power. It is that value of the voltage or that value of the current which relates to the power, or which is the power generating or the power producing part. So, therefore, let us first look at how the power waveform looks like. Let me consider a simple voltage source which is pure sine wave and just connected across a resistance R, just connected across a resistance R. So, this is V, and there is a I which is flowing in the circuit through the R. So, let us say V is a pure sinusoidal waveform which is defined as Vm sine omega t. So, what is I? I is V by R, because there is only one element which is R, which is in series with the voltage source. Therefore, I has to be V by R by Ohm's law, which is Vm sine omega t by R. So, let us say Im, the peak current, is Vm by R. Then I will be equal to Im sine omega t. Okay. So, just keep a note of this equation for the voltage and this equation for the current, and of course, the current and voltage are related through this. Now, let us look at the waveform of the current and the voltage together. So, we have the time axis. Let me take the blue waveform for the voltage. So, we have the voltage waveform which is like that. This is V, this is V, and let me take the red waveform for the current. We have, let us say R is greater than unity, and therefore, so they are the voltages and the currents. So, they are pure sinusoids. Of course, while drawing could be a bit jagged. Now, this is the current voltage and the current waveforms. Now, what is V into I? The voltage into the current is going to be the power P, and that is having a units of watts. So, the volts into amps, volts into amps is watts, the power. So, instantaneously you take the voltage at that point of time, the current at that point of time, multiply, and then you plot the power waveform. So, you see that when this crosses 0, when the current crosses 0, voltage also crosses 0, a minus current into a minus voltage will result in a positive power. So, which means that the power waveform is always going to be positive, and this will, let us say, rise like that, go towards 0, rise like that, goes towards 0, and so on. So, this will be the power waveform P, which is equal to V I. So, if you look at the power waveform, power P, which is equal to V into I, this is nothing but Vm sin omega t into Im sin omega t. This is equal to Vm Im sin square omega t. Now, we have the trigonometric relation sin square theta is equal to 1 minus cos 2 theta by 2, or cos 2 theta is equal to 1 minus 2 sin square theta. So, if we apply that, we have Vm Im 1 minus cos 2 theta by 2, which is Vm Im by 2 minus Vm Im by 2 into cos 2 omega t. This is omega t. So, if you look at this equation, you see that there is a DC term and then there is an AC term. So, here you see that there is a DC term and here there is an AC term, and the AC term is having twice the frequency, 2 omega, twice the frequency as the one that the voltage or the current that you started off with, which is having a frequency of omega. So, if you go back and look at the power curve, you see that there is a average quantity, this is the DC term, and then there is a varying AC term quantity, which is having twice the frequency as the fundamental. You see there is one complete sine wave for this period, by then it would have completed 2 sinusoidal waveforms in that period. So, there is a 2 omega or twice the frequency term which comes into the picture, which is the AC term here. So, that is one of the feature of the power curve which you should take note of. Now, if you draw only the power curve, versus time, power, which is equal to V into I. So, there is a DC term. So, let me write it in dotted, blue dotted here. This is the DC term, which is Vm Im by 2, and there is a varying term or the AC term, which starts from 0. You have a kind of a waveform which is like that, sinusoidal in nature, about the DC term. So on it keeps going. So, if you take this point to this point, that would be t 0, this is t. So, this point would be t by 2 and that is point t. So, you have two sine, this is one and this is the other, this is the other sine which you see in a period. So, this is the power curve. Okay. So, let us see this power curve and try to get the average of this one. So, what is the average? P average, which is equal to 1 by base, which is the time period for the whole time period, integral 0 to t v into I dt, which would be 1 by t integral 0 to t Vm Im by 2 1 minus cos 2 omega t dt. So, Vm being a constant, Im being a constant, we can bring that out. So, that will be Vm Im by 2 t integral 0 to t 1 minus cos 2 omega t dt. Now, if you look at the integral of this, it is pretty straightforward. Let me select that, copy. So, if you see the integral of this is pretty straightforward. This is nothing but t with 0 to t minus sine 2 omega t by 2 omega from 0 to t. This of course is multiplied by Vm Im by 2 t. So, here if you see, this is t minus 0, that is t, and sine t, that is 2 pi by t, which will result sine 4 pi or sine 0, both are 0, and therefore, this will be 0 at both the limits, and this means that we have Vm Im by 2. This is the average power, P average. Now, we know that Im is equal to Vm by R. So, which means P average is equal to Vm square by 2R, or substituting the other way, which is also equal to Im square by 2 into R. Look at this equation. Power which is equal to either Vm square by 2 R or Im square by 2 into R. So, let us take the case of P average which is equal to Im square by 2 into R. So, this is amp square into ohms, which is giving you watts. This could also be split into amps into ohms equivalently to give you volts into amps, which is the watts. Now, here there is a term Im square. There is a term Im square by 2. Let us split that. Let us take the square root of that one. So, what happens? You have Im by root 2 into Im by root 2 into R. So, you have amps, ohms. These two together is going to be volts, which is going to give you amps into volts power, or amps square into ohms, which is power which is in watts. Now, this current, which is what is equivalently producing the joule energy loss across the resistor, or which is basically the energy that is put into the resistor, is the equivalent current component that is the power giving or the power generating, and this we call the RMS current. Why do we call the RMS current? So, this is the next topic that we need to take up. So, which means this can be written as I RMS into I RMS into R, or I RMS square into R, where this is nothing but this value Im square by 2, and therefore, I RMS is equal to Im by 2. I RMS equals Im by root 2. Likewise, by the same argument, we have V RMS, which is equal to Vm by root 2. Now, let us come from the integral point of view. Let us say power average, that is, which is equal to 1 by T integral of 0 to T Vm sin omega t into Im sin omega t dt. Let us replace this by Im into R. So, which is 1 by T integral of 0 to T Im into R sin omega t into Im sin omega t dt. So, we see here 1 by T integral of 0 to T Im square sin square omega t dt into R will result in the power which is watts. In the case of the sinusoidal wave shapes, you see from here R can be taken out, it is a constant, and then you have 1 by T integral. Now, this we saw, this portion we saw was equal to I m square by root 2. Sorry, I m square by 2. So, this is I RMS square. Now, if you see, look at this equation here, what do we see as you progress through this current equation? You have a mean 1 by T integral 0 to T I m square sin square omega t dt, which is I square. So, this is amp square and this is ohms. So, RMS has to be equivalent to the root of this circled equation. So, which means if we write that down, IRMS is root of whatever was written in the circled portion, because that is equal to I m square by 2, that is amp square. So, which means 1 by T integral of 0 to T I m sin omega t square dt. So, here if you look at this equation, there is a square root and therefore, you are talking of the root, and then you have the division by the base, which is the mean, you have the mean and the current being squared square. The root mean square is basically what comes out in the progression of the equation as you do, as you write from left to right, the root mean square, or you take the square of the current, the mean and the root going the other way direction. So, that is what the RMS means, and that is the power generating component, and that is the one which is equivalent to the power generating component. So, power is equal to I RMS square into R always in the case of sinusoidal quantities, or it is equal to V RMS square by R if you are taking the voltage across the resistor. Now, if you integrate this, you should be getting I m by root 2. So, let us just verify that. So, IRMS equals square root of 1 by T integral of 0 to T I m square sin square omega t dt, which is equal to square root 1 by T. Let us take I m square outside, integral of 0 to T, this is nothing but 1 minus cos 2 omega t by 2 dt square root, which is equal to square root of the mean 1 by T. I will put I m square, we can take out the 2, integrating 1, that is T from 0 to T minus sine 2 omega t by 2 omega 0 to t. This results in t, this results in 0. Then t and t cancels, which gives you I m square by 2. This is the inner one is I r m s square. If you take the root of it, which will be I m by root 2. So, even if we come from the integration side, we will end up with I m by root 2, and that is your I r m s value. So, in the sine picture, if you draw the sine wave, with respect to time, let us say the voltage waveform, we draw this sine waveform, and if this is V m, the peak value, we have the average value, let us say, of the full wave rectified let us say that is 2 V m by pi, and let us have the RMS value slightly higher, and that value is V m by root 2. So, this is the RMS value, and this is the average value of full wave rectified waveform. Full wave rectified waveform, and that is the peak value. So, here some definitions are in order, you will see that in the literature. One definition is the peak value by the RMS value, root mean square value, which is, let us say, V m by V m by root 2, which is root 2, which is 1.41 approximately. This is peak by the RMS value. There is also another ratio, which is peak by the average value, which is V m by 2 V m by pi, which is equal to pi by 2, which is approximately 1.57 or so, half of 3.14. This is the peak by the average value. Sometimes this is called the form factor, and this is called the crest or peak factor in the literature. Of course, the nomenclature is not so important, but what is important is the ratios of these things. There is one more ratio probably you could remember, that is the RMS by average, which is Vm by root 2 divided by 2 Vm by pi. So, Vm goes off. So, this results in pi by 2 root 2, and this is approximately 1.1. So, the ratio of the RMS to average is 1.1. So, these are some of the definitions that you need to know, and the full picture of the sine wave is something like that. You have the full sine wave defined, and it has two important parameters. As you see, one is on the x axis or the time axis, and that is the period t, which is equal to 1 by frequency, and the radiant frequency omega is given by 2 pi into f, or which is equal to 2 pi by t. And the other is in the y direction, which is the peak value or the crest value, which is Vm. You could also take the peak to peak value, which is 2 times Vm, and then there is an average value. The average value of the actual sine is 0, because the positive area cancels with the negative area. The average value of a full wave rectified sine wave, meaning taking the absolute value of the voltage waveform, will be 2 Vm by pi, or 0.637 Vm. The average value of a half wave rectified waveform would be Vm by pi, which is half of that value. And then there is an RMS quantity which we saw. The RMS quantity is something that relates to the power, equivalent power producing or power generating quantity. See, the power is in terms of voltage square by R, or it is amp square into R. That equivalent voltage is called the RMS voltage. So, it is V RMS square by R, or it is I RMS square into R. In fact, in the wall socket ratings, what you see, the 230 volt rated, the rated voltage or the rated amps, 5 amps or 6 amps or even 15 amps socket, the amps that relates there is the RMS quantity, not the peak value or the average value. So, what is mentioned in all the wall sockets and all the power rating or the nameplate ratings are generally the RMS quantities, because they relate to the power. So, the RMS values are pretty important there. So, the RMS value of the voltage waveform is Vm, that is the peak value, by root 2, that is 0.707 times the peak value. So, this is 0.707 Vm, 70%, about 70% the peak value. Or the current is also represented in the RMS value, because I RMS square into R is the power. So, I RMS is Im by root 2, and the power is Vm Im by 2 or V RMS into I RMS. As we saw that power is Vm Im by 2, let us split it into RMS, which means Vm by root 2 into Im by root 2. This is V RMS into I RMS. So, for sinusoid, the power is equal to V RMS into I RMS. Note that this is for a resistive load that we have been defining it. For other loads like the inductive or capacitive loads, we will look at it much later in a later class. For now, this is how the sinusoid looks like, and try to understand the concepts of the sine wave, because you will be using that frequently in the future circuits. Thank you.